All right, welcome everyone to our March edition of Symmetry in Newcastle. We have 3 speakers today, and the first one is Michal Ferov from Newcastle itself, and he's speaking about automorphism groups of Cayley graphs of Coxeter groups. When are they discrete? Go ahead, Michal.
All right, thank you, Stefan, and everybody. I would like to thank myself for giving myself the opportunity to speak at this seminar. I love saying those things. Anyway, so this is what my talk is going to be about automorphisms groups of Cayley graphs of Coxeter groups. So the theme of today supposedly is buildings, which is very much true after lunch. In this case, it's partially true because a Coxeter group is kind of a thin building, so it's a building that is very uninteresting from some point of view, but still there's some interesting stuff that can be done about it, so I would like to discuss that. So, just a disclaimer, everything I will say today is a joint work with Federico Berlai, who's a postdoc at the University of Basque Country in Bilbao. And also this is a bit of a disclaimer that this project started as something to get my mind off things during lockdown, and it actually turned out to be very interesting. So I'd like to share some parts of it that I think are quite nice. Right, so it's just a bit of motivation. So if I have graph, which is locally finite, meaning that every vertex has only finitely many neighbors, it's connected. So then the group of automorphisms of that graph can be equipped with a topology. So it's a topological group. If you've heard it before, it's usually the pointwise conversions or the permutation topology, and the base of neighborhoods of the identity are the pointwise stabilizers of finite sets. And when you write everything down, you find out that this is compactly generated, second countable, totally disconnected, locally compact group. So when we're talking about topological groups, one natural question is when are these groups actually topologically interesting? So there's 2 examples here. If I have just a square grid, when you think about it a little, you can immediately write down what the group of automorphisms is, and it's not topologically most interesting because it's discrete, it's countable. Whereas if my graph is a tree, then I have an uncountable group, and it has actually a lot of there's a lot of topology, and still there are many things that are not known about these groups, and it's a very active and fruitful area of research. So this links us to a natural question. If you give me a graph, can I decide whether or not the group of automorphisms of that graph is discrete? And this is like an ill-formed question to start with, because how does one give an infinite graph that requires an infinite amount of information to be passed on? So you need to be able to pass that graph with some finitary means. And then also, what does can we decide mean? So usually you want to be able to either formally describe an algorithm or some procedure that once you inspect the graph or the finite description of the graph that you are presented, you can decide, make some decisions. So in general, my opinion is that such answers cannot be answered, and I think if you think about it, most likely one should be able to embed some non-recursive stuff into this problematics. However, if we can restrict our attention to some specific class of graphs, then we can get some reasonable answers. So in this case, we'll be looking at Cayley graphs because they are vertex transitive, which is a nice property. So from every point, they look the same. And Cayley graphs of what? Well, Cayley graphs of Coxeter groups, because They are nice groups. There's a fair amount of study already done about their combinatorics, about their geometry, and in this case, we find out that there's a certain property that there's certain nice things that we can say about their Cayley graphs. So, and yeah, in this case, we can fully characterize those that actually have some interesting topology connected to them in terms of symmetries of the defining Coxeter system. So, I will now explain what all these things mean, show, and hopefully we'll get to the end of it. Right, so just to quickly recap what a Coxeter group is, I think you might hear that again soon, later today, from the other speakers. So at least they will not have to spend that much time on the definition, though my definition might be slightly different. But the idea is that I have some graph, and when I say graph, I usually mean simplicial, meaning that the vertices form a set and the edges are subsets of vertices of size 2, so there are no loops, and the edges are unoriented, so there are no multiple edges, there are no loops. So that is a simplicial complex, or that the graph is a one skeleton of a simplicial complex. And I also have a function that works on the direct product, or on the Cartesian product of the vertices, which we call weight, and we want some properties for that. So first, I want it to be symmetric. So if I switch the vertices, the number is the same. If the two vertices are actually the same, the number is 1, and the number is infinity if and only if the two vertices actually do not span an edge. So then we have a Coxeter group, so it is a group generated by vertices of my graph. Well, the relation is that if I write the two generators next to each other and iterate that product weight times, I eventually get the identity. And if it's infinity, that means there is no relation. And yeah, that's it. So these graphs, this is just like I feel it necessary to say, these are not the same graphs as you would normally hear be labeled, be referred to as Coxeter graphs or Coxeter diagrams. They're slightly different. I mean, they're equivalent, but they're slightly different. So I think in my case, there's an edge exactly if there is not an edge in the other one, or something along those lines. So let's just run through some examples. So if I have just a path of length 3, and I have these two weights, these 3 weights, this is what the Cayley graph will look like. So I have these squares and hexagons being glued together, and it kind of forms this infinite snowflake, I could say. So it just keeps growing, and it's like a hyperbolic space. And when you think about this for a bit, you can see that this will actually be the group of automorphisms of this graph is actually discrete. Because once you place one of these faces, everything has to just follow. Because if I just grab this hexagon and put it somewhere else, then there's no flexibility where I put other things. Everything suddenly falls down. So I kind of have tendency to say that these things are flat, even though that they're not flat in any word of the sense flat that most people use. But it's just, it's kind of feels flat because, you can't just roll it out and it all falls into place. Or rigid if you want, which also does not necessarily follow the standard use of the word rigid that is being used. Another example, in this case, when the defining graph looks like this, and if I omit the numbers, that means I assume that the number is true, so that it's a right-angled Coxeter group. So then you can see that these three guys give me this little cube, because these three guys actually generate a group of order 8. This is the threefold product of the cyclic group of order 2 with itself, so it's really a cube. And then these two generate the group of order 4, or actually I could be super fancy and call it the Klein 4 group. And that in the end, this is an amalgamated free product of those two over subgroup of order 2. And the Cayley graph looks like this. I just have these cubes going out, and every corner of the cube will have a square attached to it, and that has another cube. And now you can see that this one actually has uncountably many automorphisms, because you could think of like, okay, I'll just like choose this infinite series of cubes, and in each cube I can decide whether or not I reflect that cube whether or not I make some reflection in that cube, say this way. And yeah, that's perfectly fine. You can do that. So that means like you have uncountably many choices, so that you will get an uncountable group of automorphisms. However, also like just looking at this, you can clearly see that this is just like the previous example, this has infinitely many ends. So one could be tempted to say, infinitely many ends is necessary. Well, not true. However, the examples that are one-ended are very difficult to draw, so now I will need you to use your imagination a little. So there's a third example where I have 6 generators, and right, so this is a slight mistake on my part. This is 2 W, gamma 1. All right, so these 4 generators, they give me this kind of, again, snowflake-ish, flat snowflake. And these 4, if I were just to think about these 4, they generate a group whose Cayley graph looks like this column, just cubes stacked onto each other. And again, it's an amalgamated free product. And what happens, how do you actually get that? You take this column, grab this gray bit, or grab this infinite line, and attach this to this infinite line going on the inside of here. And then you do that for everyone. For every such an infinite line that alternates orange and purple. So this one, this one, this one, and there's infinitely many of them. And then to each edge, infinite edge of that column, you attach another of these snowflakes, and so on and so on. It's like, when you describe it, it's, well, I don't want to say easy to imagine, but imaginable, but it's undrawable. And anyway, yeah, so this is an infinite example, this is an example that has only one end and does not split as a direct product. And when you think about it a little, you can actually you can find out that yes, this will also have uncountably many automorphisms, because you can reflect through the planes going through the middle of those columns, for example. And you can pick infinitely many columns and just do that. So those were the examples, and I would like to somewhat formalize these ideas and to actually just give you the idea of what we proved. So with Federico, we proved that if Gamma is a finite weighted graph. Well, C gamma, which is called the Cayley graph. And yeah, W gamma, I use W because it's the Weyl group, or would be referred to as the Weyl group. So the group of automorphisms is not discrete if and only if there exists some vertex in my defining graph and a non-trivial automorphism of the defining graph that fixes the star of that vertex, meaning that it fixes that vertex and all its neighbors. And if there is no such thing, then I actually get a description of the group of automorphisms of such graphs as a semi-direct product. Which is pretty nice because, it's not just I'm telling you that it's discrete, I'm telling you what it looks like. And just to sort of emphasize on the subtlety, so if you consider, because there are other groups that you can define by certain diagrams, and one of those are right-angled Artin groups. Then that was done by Tom Taylor, who was a master student here at Newcastle. So he showed that in the case of right-angled Artin groups, the group is discrete if and only if the graph is not a complete graph. So as soon as there are two vertices that are not connected, that's enough to conclude that there's uncountably many automorphisms, that you get some non-trivial topology. So that's a very different setting. So because originally, I was thinking, oh, let's just do it in the context of right-angled Coxeter groups, and it should be the same, identify some subgraph that if it's embedded in there, that's enough. And we find out that no, that's not the case at all. So, well, actually, we proved something else. So, we proved something slightly stronger, and the statement that we have is that more of a corollary. So, what we show that, if we have, we study how big the vertex stabilizers are. In how many ways can you stabilize the vertex in such a graph? And we show that, well, the star condition is sufficient to have uncountably many stabilizers. And how does that tell me anything about the topology? Well, the thing is, vertex stabilizers from the definition of the compact of the permutation topology are compact open. So an infinite compact set cannot be discrete. So that's really all there is. So now in the how much time do I have? Yeah, about 30 minutes, I guess. So I would like to run through how we prove these things to give some ideas. So, and there are some concepts that we use. So the first concept is the idea of local action. So if I have some automorphism of the Cayley graph, so I can pick a vertex and take a look what is happening just around that vertex. And if I just go back a little, yes. For example, here, if I just take a look at what the neighborhood of this vertex look like, if I think about it, that yeah, actually I have this space here, I could glue a disk in, imagine that there's an actual disk filled in this space, and in this space, and in this space, and in this space, and then I make a small ball around this vertex, and take a look at the intersection of that ball with all those faces. I would see exactly this. Because I have this blue is here, and it's connected to the green, yeah, exactly here. And then this green is connected to red, and purple, So I do get the triangle, and these would be connected as well because the face is in there. And even if I go back a little, here I could actually imagine that I write in the middle of each of those faces, I write down the number of edges that I see around that face divided by 2, and then I really start seeing my graph, including the weights. So really, at each vertex, at each vertex I see, at each vertex of the Cayley graph, I see a copy of my defining graph. So then I can ask, okay, if I map this vertex somewhere else, what happens to that? What happens to the neighborhood? What happens to the local vertex, to the local graph I see? So formally, you know, I say that here, I have this map sigma. Yeah, so the sigma takes a automorphism in a vertex and gives me an automorphism of the defining graph. So it's really a bijection on the vertices, not only that, it's an automorphism of the graph. And so then not every configuration of the local actions can appear. There are some conditions that need to happen. And that is that if I take my vertex and move along a generator, those two must agree on the star corresponding to that generator in the. And when you write it, it kind of does not necessarily come strikingly obvious, but when you start drawing a picture, it actually is way more obvious, because here I have my V, and alpha takes it here, and now imagine that X goes up this way, and then Y, then V has these neighbors labeled by these two generators. Well, I mean, then thus this square must go to a square. You know, I cannot just rip the square up. Or I cannot map a square to a hexagon or something. So really, what's happening in here fully determines what's happening here on the other side. So that really, all the edges that are connected that share a face with my generator X, what's happening on the bottom or at the bottom of this edge, the same thing must be happening at the top. And that's all there is really, but writing it down formally is a bit annoying. So now we can think about what kind of local actions we can see. And so we define two types of automorphisms of the Cayley graph that can happen. So first, a translation. That is that if the local action is everywhere the identity. So I'm calling it translation because it really corresponds to group theoretical left group translations. You know, the group acting on its own Cayley graph by translations. And an almost translation, if it's translation modulo turning around somewhere. So basically, not the local action is constant. It does not necessarily have to be identity. So, you know, I move things around, but that's also like I do a move, but I do the move everywhere in the same way. So if you think about that, say, something simple as just the Euclidean plane, you know, not only I move the plane, but I also turn it around, but the turn is everywhere the same. This might not be the best idea because, or the best example, because I do not really have the option of not turning around somewhere if I do this with the Euclidean plane. But if you think about that, say, in the context of a tree, you know, not only I move the tree somewhere, then whatever I've done to the colors that I see around the vertex, I have to do it in the same way everywhere. And naturally, we can ask, how do these two types actually sit inside the automorphism, group of automorphisms of this big graph? And it is somewhat how you would expect. So just a group of translations is isomorphic to the Coxeter group, and the group of almost translations is isomorphic to the Coxeter group semi-direct automorphisms of the local graph, which kind of you would expect, because I move something around and then I turn it by a local symmetry. Showing it is a bit, well, it's not tricky, it's just a bit tedious, but really in a sketch, first you identify the W gamma, the Coxeter group, with just the translations. That's just checking a couple things. Easy. This one is a bit tricky. So the automorphisms of the defining graph you identify with almost translations that fix the origin. And when I'm saying the origin, I mean the vertex of the Cayley graph corresponding to the identity. Since the thing is vertex transitive, it doesn't matter. You can pick your favorite vertex, but it's just I'm saying the origin because I'm used to saying that. But yeah, so identify the group of automorphisms of the defining graph with exactly those that fix the origin and have constant local action. And then you need to check that it's actually those three properties that you would want from a semi-direct product. So first, you want to check that they actually generate all almost translations, that they intersect trivially. You can kind of see that from the definition, because the only translation that fixes the origin is the identity. And then checking that this is a normal subgroup. Again, it's really just like writing down the definitions. So nothing too complicated. So now the second concept that we use is the concept of a separating set, or a thing also in combinatorics they call it vertex cut. So the idea is that in my defining graph, I find some subset of vertices such that if I remove it, my graph becomes a disconnected. And now the special case of separating sets that we are interested in, or that we use, are called good separating sets. This is our terminology. I'm not entirely sure if calling them good is the best. If you have better, let me know. But anyway, the idea is that the separating set is good if you can find, if you can split your graph into two bits such that there's a non-trivial automorphism moving one part around but fixing the separating set. So here's a simple example. Another example would be something super silly. So for example, this is a good separating set because it disconnects my graph into this square, into this triangle, and I can either flip this part or this part, but I'm fixing this. And if I go back a little here, you can see that this would be a good separating set because I can flip these two without touching this, without actually having to move these two vertices. Oops. Yeah, there we go. Right, and this is just like some combinatorial characterization of when can a graph admit a good separating set. It's just several equivalent statements, or several statements that are equivalent. So admitting a good separating set, admitting a vertex such that the stabilizer of its star is non-trivial, or admitting a set, a separating set and two automorphisms that move things around and agree on the separating set, or that move around one half of the graph and fix the separating set. And you can sketch the proof, it's super easy. Like if I have something that fixes a star, then clearly the link, all the neighbors of that vertex form a good separating set, right? Because they separate the vertex from the rest of the graph, and you can move the rest of the graph, and the link is not moving. Similarly, like if I have a good separating set, then I have some alpha that moves around those two potatoes on the top, or three. Then, I can pick some vertex in the bottom potato, and clearly its link must be included in the whole bottom potato. So it's the same thing. Again, so I'm able to fix those. And also, if I have two elements that move things in a different way, but they agree on the set, I can just take their difference. And that thing still moves something non-trivially because they have to differ, but it fixes the separating set. It's like no hard thinking really here. It's just writing down the definitions. And it's just that at different parts of the proof, different definition is easier to work with at that point. All right, so, and how actually do the good separating sets play a role in this? So, it's basically two statements. So first we go there. So, if we have a good separating set, then we can construct uncountably many elements that fix the origin. And then we go back again. And if we don't have a separating set, then actually all we can get are almost translations. And you see it's there and back again. Those of you that have met me know that I'm obsessed with Lord of the Rings and stuff like that, and I kind of think it's there, because first you go there and you don't really know what's happening or what's going to happen, but you have some expectations, and then you come back with way more than you were expecting, just like Bilbo went for an adventure and suddenly he came up with a chest of gold. So yeah, like, not only did we show that it has to be discrete, but we get some structural information about the automorphism group, which is a nice bonus on the side, just like the chest of gold. All right, so how does that go? How does that go the way going there? Just finding out the infinitely many, uncountably many automorphisms. So first, one thing to notice. If I have a separating set in my defining graph, my Coxeter group splits as an amalgamated free product. So I can find some subsets that kind of are arranged in a tree-like manner, which is exactly what the next. Yeah. Then also, if it's good separating set, I can make some automorphisms on one. I can make some non-trivial automorphism on one part of the defining graph that does not move the rest. So now the idea is that I take the Cayley graph and slice it up to the cosets corresponding to the first group, to the first factor. Yeah? These guys. They are connected through, of course, like it will look a bit different. It will be, if you wanted to draw that, it will be a tree from basic Passer theory. But they are arranged in a tree-like manner. There would be another one going here, but it will not intersect any of those, and then there will be another, so on. And now the idea is that they intersect through these bits, where they actually through these bits, and these correspond to the WS. the group over which we're amalgamating. So that's just how we should think about that Cayley graph. It's this bunch of subspaces, and then we are connecting them. If I go back to I should have copied that just. If I go back to this example, what I can think of is that I have these cubes. All these cubes are the cosets that corresponds to this triangle. So all these cubes correspond to this triangle, and I have all these squares, green and blue squares. And at each of these cubes, I can decide whether or not I'm flipping through the middle. So what do I mean by that? First, I pick one reference point, my origin vertex. I'm fixing that one. And then at each of these cubes, I decide whether or not I'm flipping through the middle or not. So then I have infinitely many points where I can make that decision. Because if I'm just going here, and then I know, well, I might be not through the middle, but I would be switching these two vertices, so that means I will be switching these two. So it will be a reflection through this plane going through this cube. All right, I'm all the way back to where I was. No, not yet, almost. Yeah, almost. Okay, there. All right, so for any subset in the coset space, I can construct an automorphism that does that. So I have this many ways to do that. So that I know that the stabilizer of the origin is at least this big. And this is perhaps not obvious, but this will be always infinite. I mean, it's a third decomposition. This is a decomposition as an amalgamated free product, so there has to be infinitely many cosets. So this will be always infinite. Right, so that's one way. It's not too difficult, but writing it down is a bit annoying. And going the other way is super easy. So suppose that I have something that is not an almost translation, right? Then I have some automorphism that does one thing somewhere else, and one thing somewhere, and different thing somewhere else. Well, that means that, that's what I just said. I have two vertices that locally get different things done to them. Well, we may assume that they're neighbors because use some induction argument, take a geodesy between them, keep going on. We can assume that they're neighbors. But I mean, we know that what they agree on, that the local action must agree on the star. So whatever's happening there, I guess people who are connected online can't really see my hand waving. So I'll just draw this in. So suppose that here's my V, and here's my W, and it's connected through X, and that here the action is some alpha, and here the action is some beta. Well, then actually I can just verify from the definition that alpha inverse beta fixes the star. That is non-trivial, which means that the star, or not the star, but the link of vertex x in the defining graph must be a good separating set, which means that existence of something that is not an almost translation already implies that there must be uncountably many automorphisms from the previous lemma. And so that's what I wanted to say, and it's just like more of a discussion that, you know, you can go hard or harder if you wanted to. I don't really want to, but I feel like, you know, the tools are already there. So, you know, I could care about graphs that are not necessarily finite. I can take graph, I don't want to draw, I want to highlight. So I can take a graph that has, you know, arbitrary cardinality and still ask whether or not there is a separating set, a good separating set. If there is not a good separating set, you know, I can take a, so what I'm saying, I would take a Coxeter group that is infinitely generated, you know, it would be potentially, you know, the size of the generated set could be any cardinal, but still, I get some structural information about the automorphism group of that infinite graph. And that is, if there is no good separating set, it must look like this. The Coxeter group, semi-direct automorphism group of the defining graph. If there is no good separating set, and if there is a good separating set, then I know that the vertex stabilizers are at least this big, whatever this cardinal will be. And I guess you could get some non-trivial statements about groups, topology. I guess these will be Polish groups, some kind of groups acting on a graphs that are very big. There still is some topology, you still get permutation topology, but it's complicated. I know very little about it. I don't want to talk about it on us. But anyway, if you feel like doing it, be my guest. I will just say that this is what you can what you can do, but I shall not fret these waters. So, and that's all I wanted to say.
All right, very well. Any questions or comments for Michal?
Yes, George?
Concerning your last theorem,
this one.
yeah.
Oh,
Can you give a condition on the graph that says that the automorphism group is locally compact?
on this graph,
Yeah.
well, I mean, the local compactness you want, if we are assuming that there is no actual topology associated to this graph, that it's really seen as a discrete space, you know, its vertex space is discrete, and you know, to make it locally compact, you want the vertex to be finite, right? But you could perhaps get some more complicated stuff if you assume that there's some topology associated to the vertex set, or you know, each neighborhood of each vertex has some sort of topology. Then yes, you could, I guess, one could, probably not me, or definitely not now.
I guess it would be that in the permutation topology, you want the star fixators in the automorphism group of gamma to have finite orbits on gamma.
Yeah.
And then they'd be compact.
Yeah. Or maybe not finite orbits, but compact orbits.
Well, I mean, in the permutation topology, so you just
Right. But yeah, if you want it to be locally compact, you need the defining graph to be finite. And then I guess like some other things could happen if you actually assume that this graph has some topology and you're acting on by homeomorphisms. I would prefer not to go there because I have very little understanding of what's happening there.
Well, what you say about there being a topology on gamma, that's also a good thing to think about. But what I was wondering was actually what Michal said. You've got a condition that guarantees that the topology is discrete, but maybe there's some condition on the action of this fixator of the star that implies that it's non-trivial, but still.
Oh, okay.
Locally compact.
Yes, right. Oh, okay, now I see what you mean. Because we could have, say, if these were countable, then yeah, design the graph so that yeah, the action of this thing as local orbits, finite orbits. Is that what you're saying?
Yeah, I mean,
or the stars?
Obviously, you want all gamma to be locally compact, which doesn't mean it has finite suborbits, but it means that there's some, like, you fix enough points, you get finite orbits. And specifically, you want the fixator of the star to be compact.
Yeah. Yeah, that sounds likely. I will admit that Federico and I haven't really thought about that much. Because initially, like, I thought, oh yeah, let's do it in full generality. Then I realized what that would mean and decided, yeah, let's not do that. But yeah, there is obviously some research to be done in the non-finitely generated case, but we haven't really thought about that much.
And if you go back a couple of slides,
how many?
previous slide. Yep. So these elements here that act as alpha at one point and then identity everywhere else. I'm wondering how close they come to giving you a topological generating set for the automorphism group. Just thinking about the analogous statement for groups acting on trees. Because you have these almost translations and then you have these elements that sort of act independently at each point.
So I think you might be able to construct a generating set like this. However, you would need to consider all good separating subsets. Because there's an option. It could happen that you have some sort of action here, and then as the graph forks out, you can start doing different things here and different thing there. So so that different good separating set that action at this part of the graph might correspond to a different good separating set. And it is one thing that I was thinking that would be interested to look at. Basically, that would correspond to Passer theory the Passer theory of this Coxeter group. Basically, consider all its actions on a tree, in how many ways it splits. Because, for example, for right-angled Artin groups, there's a full classification when a right-angled Artin group splits as an amalgamated free product, and that is if and only if it splits in an obvious way, meaning if you can find a separating set in the defined graph. And there is no such statement for Coxeter groups, but I think that it could be achieved. It's just that the statement for the right-angled Artin groups relies heavily on like Haglund-wise stuff, which does not necessarily apply once you start doing things that are not cubes. But maybe in the case of right-angled Coxeter groups, it might work. Because then, just looking at the defining graph, I could identify all those separating sets, and I know that that's all those things that can happen, and that no other action on the tree interests me or can happen. And then, can look at some sort of hierarchy. And I think the term that one should think about is tree of cylinders, how you can connect the separating sets in a chain so that things can fork out, and you can see like how the local action changes as you spread through the graph. But this is more of a wishful thinking and building castles out of thin air than an actual mathematical idea. It is an idea about mathematics, but it's not very solid.
I thought the separating sets were in gamma, so you're still talking about finding many things.
Yes, but true, but what I was saying that in terms of right-angled Artin group, that splits if and only if it splits the way that you can see in the graph. And it is not known for Coxeter groups, but it would be nice because then you can see that you can kind of employ some JSJ decompositions and that kind of stuff. But I haven't thought about that too deeply. I've been thinking about different aspects of these things.
Yeah, I don't know. It might be easier than that. there might be an easy way.
Yeah.
So,
Right.
Any other questions or comments?
Yep.
On that?
Can you say anything about the global structure of these groups? For example, if you have different defining graphs, can the groups be isomorphic?
Oh, yes, I forgot to put that in. But yes, we do have statements about so-called rigidity. And that is if my defining groups or defining graphs give right-angle Coxeter groups, right-angle Coxeter groups are rigid, meaning that two right-angle Coxeter groups are isomorphic if and only if their defining graphs are isomorphic as graphs. And we also showed that the automorphism groups of the Cayley graphs are isomorphic if and only if the defining graphs are isomorphic. And I think, well, I'll be honest, Federico wrote that part of the paper and I haven't proofread that bit yet. So I'm a bit hazy on the details, but I think the statement is that whenever the groups that we see, the Cayley graph, whenever the Coxeter groups that are in question are rigid, meaning that they cannot be given by two non-isomorphic graphs, then the group of automorphisms of the Cayley graph are isomorphic if and only if the graphs are isomorphic. Just to give an example of what I mean by something that could not be rigid, and I will almost definitely mess this up, but yeah, the dihedral group D6 can be written as a Coxeter group in two ways. In two ways, and they give you non-isomorphic Cayley graphs. Yes, I think you do this, would this be it? And then there's it's also a triangle, like 2, 2, 2. So what do you get from this? You get a I might have messed this up, but assume that this is 12. And this one gives you like a prism, hexagonal prism.
So I think for the second one you want A3 times a point. I think you want just one, it's a disconnected diagram. I think, not a triangle, because that would be a group order, right? Yeah, that's the way.
Okay.
I think 3, 2, 2.
Oh, yeah. Yeah. So this is an example that is not rigid, but if we assume that the graphs that we presented are rigid in the sense that they give you a Coxeter group that cannot be given by a non-isomorphic graph, then we can already assume that the isomorphism on the level of isomorphism on the level of automorphism group of the Cayley graph already is sufficient to assume that the defining graphs have to be isomorphic.
Anything else? I had one question too. The automorphisms of these graphs that have trivial local action everywhere, which you call translations, they're not necessarily translations in the graph theoretic sense, right?
No, they are left translations in the group theoretic sense, but they will include reflections in a graph theoretic sense. But I'm calling it translation because it's really the embedding it's the group acting on its own Cayley graph by left translations. So it is a bit confusing, but also it makes sense.
Yeah, fair enough. All right. All right, if there's no further questions, I'll stop the recording here.